Start recording here. Let's get our good camera out. How'd they manage that? Why we can't even go visualizer? Is it visualizer on here? No, we'll go for camera then. Camera. Is it gonna work? Oh, other apps are using your damn camera. This is a problem. Let's see here. 1 second while I sort out my audio visual woes. Huh. So let's see, what do they do here? Oh, I know why, because I unplugged the camera. The camera is the microphone too. That's why. Thank you so much. Sorry guys about that. So that's going to make for a great video. Dylan had a request for, well, they're numbered differently here. Which one were you asking for? The airplane? Yeah. That one right there. Okay. So that one's number 20 on here for some reason. Inexplicable reason. Let's see. But I do think I have it on my page as number 5. Okay. So we have this jet fighter, and it's this weird blue thing. Here, let's see if we can make this less blue, more bright. Man, I wish that thing was bigger. All right. So a 54 kilogram pilot flies a jet trainer in a half vertical loop of 1,200 meters radius, so that the speed of the trainer decreases at a constant rate. Knowing that the pilot's apparent weight, i.e. normal force on the seat at points A and C, are this amount and this amount, determine the deceleration of the jet. So this is a problem where it kind of makes you go through a little bit of a story, right? You got to kind of like picture out a what if and a what if. So they're telling us at 2 different positions. So let's draw 2 different sets of free body diagrams and inertial body diagrams. We'll do one at A and do one at C. So we do an FBD, an IBD, and the question should be of the jet or of the person. Well, I heard this magical word on, right? And I think he's like yeah, here it is. Here's the word on, right? The normal force is on the seat, right? So it's going to be best here, I think, to draw the pilot. Make him happy. And he's a little fighter pilot, so he's a little evil. And in this case, let's make that tangent in this normal. We kind of like recognize that he's going through this loop thing, so it's probably the tangential and normal things. And here, we'll draw these on here. So in terms of forces, recommender says it's his apparent weight, right? So that's a vertical force, that 16 right here. So we're going to have that force acting right here on him. I'll call him FNA and recognize that he is 1680 newtons. We also have his weight. So this is the weight, or he's, I guess we might as well run mg, right? Because it's SI. And then also, he might have some tangential components. So I'm going to say that he's going to have like maybe a seat belt force. So I'm going to go to FBA. All right, so those are the forces I believe that are going to be on the pilot at point A. Then I go and I see, well, what kind of accelerations and well, they actually told us he's decelerating right here. So we can have intuition to say his tangential must be that direction. So we go M, AT, and maybe I'll say ATA. It's probably the same, right? See, because they did say he decreases at a constant rate. So he could be the same tangential everywhere. It doesn't matter. Here, on the other hand, we're going to assume that this A is inside the turn, right? Sometimes you might have to make that little decision. Are we talking about right before A or right after A? We're going to say this right after A, so that he's in the curved part. And therefore, he's going to have a normal. And I believe this is going to be a different normal here than it's going to be up here, right? Because they already told us there's a different force. So I'm anticipating it's a different normal acceleration. So we're going to go A right there, just to make it clear. So if I take the sum of the forces, and I don't know anything about this yet. This is actually what I'm trying to find. So it's kind of a mystery. They don't know anything about the seatbelt force. That might have helped me onto this. So I'm going to just go in the thing that I do know, and that's the normal direction. And in this position, he's this. So mass times acceleration in the normal direction. We might want to write over to the side that we know the normal acceleration is defined by this right here. So that's an equation, something that we know about the normal acceleration. So doing a sum of the forces over here, I say that we have, well, first off, I have a 1680 in the positive normal direction minus weight, which is going to be my 54 and 9.81. And there's no other, set that mass times acceleration. And I've also already drawn that in the positive direction. It's 54. So I can find my normal acceleration here. And my good friend Alicia Garcia, who wrote the solution to this, didn't bother doing the in-between numbers. She likes doing that. But I like in-between numbers. So 1680 and 54 times 9.81 and divide by 54. And hopefully I didn't mess up my calculator. 21.30 meters per second squared. So we can, from this, go, oh, I know something else about the normal acceleration. I know this right here. So from this, I can get what the velocity is at point A. Right, so I should have put an A in there. So the velocity at A is going to be equal to the square root of AN rho. Is that true? Do that right? Sure. A. So square root of 21.3 times 1200. I'm getting a little nervous about getting there. Oh no, okay, it is a large number. Okay. So 1200 multiply square root. Yeah. Oh no. What did I do wrong? I feel like I did something wrong now. Double check it. 1680 54 9.81 times minus divide by 54 21.3. Gotcha. Oh, I see. Okay, she looked at this squared. Okay, that's why. Wow, I don't know why she does that kind of thing. 1200. Yeah, okay. And then take the square root. She skipped a step. That's why. Okay. So I got 159.9 meters per second. Anybody else getting that? Okay, cool. All right. So we know one thing. We know the velocity right here. So now we can kind of, maybe our strategy starts to become clear. We might have got that aha moment somewhere along there. What we're about to do. Anybody else see where we're going with this?
So we just found the normal for A. I feel like we're going to find the normal for C. So we found the normal acceleration for A, and I feel like we're going to do the same thing for C, and then we're going to find the difference for each other, which is the real deceleration.
Yep, exactly. We're using kinematics, right? Because we're going to know the arc length of this path. So we're going to have two velocities and an arc length. So we're going to be able to use that to find the tangential deceleration.
I just have a question about rho, so I don't think my teacher uses that.
Okay, some of these are. It's just it's just a I don't know, archaic
traditional thing to use rho for some reason for the curvature, because not every curvature is a circle. So it's just the radius of curvature of something, because sometimes something can have a wide sweeping kind of thing. And so at an instant on a curve, it could have, like a circle could be found that would match that radius of curvature. So rho gets used, but you could use it interchangeably with R if you know of a circular motion. But that's a great question.
So what we do here now is for point at C, we do the whole thing over again. But this time he's going to be, or she is going to be like here. So I'm trying to. And now the force, the normal force of them felt that what they feel on here is going to be 350. So this is the F and C, 350 newtons. But we also have mg. And then we also might have, well, it depends on, yeah, I think it's going this way too, right? So we're going to have the force of the belt at C, if someone were to ask us those types of things. And then, so the coordinate system here, let's set this up, because right here at this spot, tangential is going that way, and normal is coming down that way. So we go, tangent is here, and normal is there. But we know we're decelerating, so here's going to have our m, a, t, and it's a constant, right? So this is the same tangential acceleration as this one. It's what we're trying to find. But the normal is going to be going upwards, m, a, n, let's call it c. So the sum of the forces.
Why is the normal upward?
Oh, you're right. Sorry, my bad. I made a mistake. I wasn't thinking. I turned my thinking cap off there and it was talking. You're absolutely right. M, A, N. Thank you for catching me. Give myself one more space here. Yeah, it's got to go towards the center. So some of the forces, hopefully I would have caught myself, but man, you don't know. In this case, positive is that direction by way of this normal. And so we'll have a lot of yelling going on next door. Must be a good class. I wonder what we're learning about that. Hope it's something great. No, you're right. That's a good. I like that answer. It's a good answer. So we're going to find N, A, N, C. So this A, N, C is now 350. So we have 350 and 54, 9.81 times plus 54 divided. We get 16.29. And something I should have mentioned up above, it's a good idea to kind of think about the context of what that is. Think about how many G's that is, right? You can mentally do it, or you can actually calculate it, divided by 9.81. You see, people often talk about G's when they go, especially when it's the human body, what it can withstand, right? Or what you might enjoy on a roller coaster, right? That's the whole fun part of the roller coaster is trying to see how many G's that you can experience when you go around a curve. But let's see. So we'll say that the velocity of B is now going to be the square root of A, not B, C. And then rho or R if you want to. And so we had 16.29 and 1200. So let's see, 1200 times that. Take the square root, boom. I get 139.8 meters per second. Two velocities are been able to been found on this arc, one here and one here. So it's traveling this distance. So that's that's actually just 1 radian, or pi radians, excuse me. That's pi radians. Right? There's 2 pi radians in a circle. There's a half circle. So we could find this arc length. You can always find an arc length. So let's call this delta S, if you will, by multiplying the change in angle times the radius. Right here. And so in this case, that change in theta is going to be equal to pi. Right? 180 degrees equals pi. So delta S, delta theta R, or pi times 1200, and we left with a large number, 3,770 meters. So we go back to kinematics, constant acceleration kinematics, and we say V, let's label it C, is equal to VA squared plus 2 times the tangential acceleration times the change in position, which is along a curve. So we have 139.8 squared equals 159.9 squared plus 2. Here's the thing we want to get, 3,770. And what we end up finding was we'll get a negative value, right? Because that's going to be larger than that. So I manipulate my stack here. Square, flip it around. Square. Ooh, that's not good. And I have to enter in my numbers again. 39.8 squared. 159.9 squared. Subtract, get a negative number. Divide by 2, and then divide by 3,770. And hopefully, yes, I got negative 0.7989 meters per second squared. And that's what she has presented as the solution. I have a tendency, I guess that's fine. I don't like using, I most of the time would ask for an arrow instead of a negative sign, but that's fine. I mean, we're kind of talking about deceleration, so there's actually sort of a little bit that says determine the deceleration of the jet, so you almost don't even need to give the negative sign. Kind of assumed it's going to be, right, something. There's a communication thing there, whatever it takes. Just don't put a negative and an arrow together. All right, so this would, I think, be sufficient to show that you know what you're talking about, but also communicating it. Yes, sir.
Could this probably be done, could the path be a different shape? For example, like from C to B, it has a radius of 1,000 meters, and then from B to A, the radius is like 600.
Absolutely, yeah.
And would we have to find the velocity at C, D, and then A?
As long as they said that it was a constant deceleration, I think we would have been fine for just finding it in 2 spots.
Gotcha.
But you would have had to maybe do a little bit of work for that arc length, because you can't just change from, well, I guess maybe you could.
You could use the arc length.
Yeah, it could. It would be, I guess, I could see that. I could picture it maybe, having, of course, people at home can't see me, but I guess you go like that, and then go like that, right there, something like that. I guess that's sort of like what you're referring to. Yeah,
Or the opposite sharper.
yeah. Oh, yeah. Okay. Whichever way. Yeah. Other questions or question type? Yes, sir.
Question on page 9, the work energy one.
I don't have to look at this, but it doesn't hurt. Hey, my good friend Sean Munnis's problem. You must use work energy principles. Okay, so we got a 7.5 pound collar released from rest. All right, so it starts out with a kinetic energy of 0. In the position shown, slides down the incline rod and compresses the spring. The direction of motion is then reversed and the collar slides up the rod. Knowing that the maximum deflection of the spring is 5 inches, determine the following: the coefficient of kinetic friction between the collar and the rod, and the maximum speed of the collar. It's a good question. All right, so it's always a good idea to draw your 2 things here. All right, so first off, knowing that the maximum deflection of the spring is 5 inches. So maybe we want to go to, from this position, we call that 1, down to the position where it gets compressed 5 inches. So we'll kind of just draw this thing out, right? We got to kind of tell ourselves a story when we're doing a problem like that. I do a great job on my drawing. And so here is right, so here is state 1, and here's state 2. A lot of times I'll draw that on the same diagram. But like right here is probably where I want to choose my datum. I'll go right here at the bottom. Right here. For one thing, from here to here was 18 inches. So from here to, let's see, this, I measured from the bottom of this, so I better measure to the bottom of that. This right here better be 5 more inches, or 23 inches. Yes, sir.
Is there a particular reason that you define the datum as like a fully compressed spring?
I like to have one because I like to have where it's going to go to the bottom.
Right, like the 0.
Yeah, I like to find the 0 location. There's some professors or people that will do it, you know, maybe start from the top, but then in order to do potential energy for gravity right, you have to have negative potential energy. All right, so but you're measuring from a datum, so that's not that big of a deal. I just don't like the concept of negative potential energy if I can avoid it. It makes more sense to me to have it as a positive thing until it gets to its minimum. But right here, we're calling that the datum. So we want to measure, and I'm doing from the center right here. We want to have this right here. We can say this is the change in Y. Sometimes I'll write from 1 to 2, right? Just to say, but we're going from state 1 to state 2. Here is the change. So in this, good thing to start writing out, you know, equal to KE2 plus PE2. And think about what each of these is going to be. I think I'll be okay with the room. I kind of like to write each of these, right? So at start right here, starts from rest. So the kinetic energy is 0. Potential energy is state 1. Okay, that's going to be its gravitational. And I could write mg, but also I could write weight, right? So I could just go W if I want to. So he is 7.5. And over to the side, maybe somewhere, I would say, well, he's moving 23 inches, but his delta y is going to be times that distance times the sine of 30. So maybe I'll write them up here. 1 to 2 is going to be 23, but might as well make it into US units. So that's going to be divided by 12 and times the sine of 30.
So we're going to be left with 7.188. And I'm partial to foot-pounds instead of pounds-feet, but either or, same thing. Good. So that's the delta. Did I do that wrong? Yes, I did that wrong because that's. I'm sorry, I just jumped the gun. My bad. I needed to do that as a in-between step. That was going to be down here. So they decided to combine it down there. I say they.
Could we have made our datum at the 18-inch mark, so it would have been like 18/12 sine 30?
Sure, but then we would have had to it would have moved down another 5 inches when it compressed the spring, right? So if we wanted to know the speed just before it hit the spring, maybe that's the place that we would do it. But because we were going to go down to all the way where the spring gets compressed, we're going to go for that. So 23 divided by 12, and then 30 sine. So I believe I get 0.9583. Looks like, I don't know why I just put a thing there. I gotta get your head in the game, man. It's really distracting, this thing behind me. 0.9583. So what we're left with, and let's go ahead, we just multiply that by 7.5. Hopefully I get the same number. Yes, 7.188. Call it pound-feet, foot-pounds. All right, so we don't know the work, but we were told there was friction, right? So we wanted to find the coefficient of friction. So maybe that's what we're going to be able to find. We're going to be able to find what the friction force is because we know the distance this thing is going to move. I'm going to call it delta S. So that's going to be equal to the 23 inches, right? So when we get to this, we'll divide 23 by 12 for this term, but we're going to look for the friction force is the thing that we're going to need to be able to get that first answer. The potential energy at state 2, it's at its datum, but it's going to be this thing is going to be compressed by del, I'll call it 2. You're absolutely right. It should be negative. So when we put it into there, make sure that's negative. Thank you. And let's see, the K, oh, they told us is 60 pounds per foot. And this better be turned into feet. So take 5 divided by 12 and square it. And 5, 12, and square. So we're going to get 5.208 foot-pounds. And then the last thing, I should have actually done this one before that one. The kinetic energy at this second state is also going to be equal to 0 because it's going to pause right there at the bottom. So plugging into here, 7.188 negative friction force times distance through which it travels, which is going to be the 23 divided by 12, needs to be in feet, equals 0 plus 5.208. So we're going to get a friction force. So we subtract that from that. And I do believe friction force is going to be 1.033 pounds. And we could do a quick little FBD. Truth is, we should probably do an FBD, IBD. But not really necessary to do the IBD because we're only doing this to establish what the FN is. And the FN actually should probably look like it's on the collar right there instead of on the bottom right in there. But I'll just kind of draw it like right to there. And then the friction force is maybe coming up that way, FF, onto this thing. And it actually kind of depends. This is just before it hits the spring, right? So I'm not going to draw the spring force on here. It probably was because it started from rest. So before it hits the spring, the acceleration was probably going down in that direction. We'll call it X prime right in here. So here's my X prime, Y prime, just to be fully clear. But we're only going to do this so that we can get the normal force. There's the weight, and there's the angle. So in the Y prime direction, mass times acceleration in the Y prime direction, that's 0. It's positive declared. So we'll say that we have Fn minus the weight times the cosine of theta equals 0. No acceleration there. So Fn minus 7.5 cosine of 30 equals 0. Fn, 7.5, whoops, not 75, 7.5, 30 cosine times, we get 6.495 pounds. Therefore, the coefficient of restitution, not coefficient of restitution, the coefficient of friction, all kinds of confusion, 1.033 divided by 6.495. And should be 0.158, actually 90. And now we want the maximum speed of the collar. So pretty much have to do the whole thing over again, but no, not too much. We really should reset all the datum again.
How do I know whether the max speed, like to take the reference as right before it hits the spring or after it hits the spring?
It's going to be right before it hits the spring, because as soon as it hits the spring, it's going to start decelerating, right? Because we know that it's going to reach 0. That's when it bottoms out on the spring.
Is it possible that the spring could build up enough energy to have its velocity be more so afterwards?
No.
Okay.
No, because it's going to have some friction in between the beginning and the end, right? So it's going to get to the very bottom of the spring, and it's going to it'd be 0, but it would already pass. And now when it gets to the back end, the spring starts pushing it back up. And so just after the spring, it releases the spring again. It will have traveled through 2 paths of friction along those 5 inches. So it would have lost energy. So it's not going to it can't have this a greater velocity after than before. I guess I'll draw the thing over here to the side. I wanted to try to fit everything on this page. So the kind of have to do like a little bit of a reset in here. So now it's just now we're drawing it state 2. This is state 1. State 2 is just before it hits the spring. So now it's datum right here. This is not that. I drew the distance wrong. So it's not the distance in between. It's the distance from this edge to that edge. This is going to be the 18 right here. So that's state 2. And so here we're going to have, we're resetting everything so we can use, reuse some of the variables here. So we're going to have the KE1 plus PE1 plus friction from 1 to 2 equals my KE2 plus PE2. We still have, this is still 0, and this is still 0. No, that's not 0. Sorry, my bad. That's not 0. Yes, potential. Oh, Jesus, it really is obnoxious. This thing behind me. Maybe it's not loud for you, but it's just very distracting. I'm gonna blame them. Somebody else's fault, right? So my PE in this case is going to be a little different because my delta Y 1 to 2 is now going to be 18 divided by 12 sine of 30. Or just 0.75, all right, duh, could have done that in my head. No, maybe not. No. So weight is 7.5 times 0.75. 5.625 foot-pounds. Maybe they didn't do it in between. Work from 1 to 2, like you said, it's going to be negative. Friction force, we already figured out that friction force should be the same everywhere. 1 point, because it's going to have the same normal force, therefore it's going to have the same coefficient of friction. So the 1.33, but now it's going to be moving 18 inches divided by 12. So 18, 12 divided and 1.033. So I'm going to have a negative 1.550 foot-pounds. My KE2 is what I'm trying to find, 1/2 mv2 squared. And then we already said that that's going to be 0. So cramming everything in here, 0 for that potential kinetic energy plus 5.625 minus 1.550 to be to 1/2 mass. Remember, you have to divide 7.5 by 32.2 to get slugs. V2 squared plus 0. So we should get V2. So I'll subtract that from that. Multiply by 2. And then 7.5 divided by 32.2. And divide. And now I get to square root it. And do I get 5.916 feet per second? Make sense? You could do this problem.
Yeah, I was having trouble because when I was doing this on my own, earlier in the for the spring potential energy, I had instead of dividing the deflection of the spring by 12, I divided the spring constant by 12.
Gotcha. Okay. It's probably best just to always stick with the feet.
Right.
Yeah, because well, mostly because the kinetic energy, you want to remember. I mean, okay, so that'd be part 1. Part A. You might be able. Let's see. Let's take a look at there. Yeah, I guess if you kept everything in inches, it wouldn't kill you. But you would need to use the acceleration of gravity. No. Yeah, because well, you already had weight in there. No, I think actually everything would cancel out. No, yeah, maybe. I can't say for sure. I think the units would maybe work out. So what you really want to keep it in feet in it for is because if you use slugs, you have to use feet for everything because slugs are a foot-based means of getting mass. Yes.
Can you go back to the problem statement, briefly? I just had a question about your redefinition of the data for part B.
Okay.
And like what is our process for applying that?
Oh, that's a good question. Well, once again, like my philosophy is I want to try to avoid having a negative potential energy, right? What I could have done, all right, so what I could have done is now define state 2. I could have renumbered. I could have started from the very beginning if I wanted to keep things consistent. I could have called this state 3, right? And then maybe just a bump above it, called it state 2.
Okay, I think that's confusing.
All right. And then what I would have then, I would be consistent all the way through. This potential energy would be correct, but now the potential energy I would get right here would be maybe the sine 5 divided by 12 times the sine of 30 degrees, right? I'd use 5 inches now from the bottom of the thing. But it's it'll get you to the same place. Yeah, it's just kind of like when my in hindsight, maybe that would be a consistent thing to do. But just when I looked at the thing, it went to my, you know what? Just going to do a data reset. It's also because I was influenced by Sean Munnis's solution here, my former colleague. He got 2 degrees from MIT.
So a little bit of bias.
I was biased. Yeah, I was already. It was implanted in my head to do it in the same way that he did it right here. And of course, he's using T's and V's because I made the decision later to go to KE and PE, but this is what the book does right now. But you see that he made a new datum down here.
Personally, I would have done it my way as you guys would.
Yeah, well, MIT guys. He's also a Wrench Turner engineer, so you can't. There's a famous video. Is that famous? I don't know. Not that famous. I think it was actually 60 Minutes. It might have been. 60 Minutes, where they showed this experiment where they went up to MIT graduates at graduation with a wire, a light bulb, and a 9-volt battery, and asked them to get the light bulb to turn on. Have you seen that? It's actually not supposed to be making fun of MIT engineers as much as it's supposed to show that how difficult it is for the brain to process something when they first see it, right? So even a very, very smart person, and also just the nature of our education system of how we emphasize some things, and we kind of get into a groove, and that's how we're able to solve problems, that are in that type of frame, in that same thing. But then, now when you present someone who's very smart and very accomplished with a simple task that they haven't seen, and they can't solve it, because what they've really become good at is solving things in one particular environment. Throw them into a new environment, it becomes hard to solve. But anyway.
Did you get the sign in we got here? I did.
No, but it'd be a good idea. Thank you. Anybody got a blank piece of paper? Anyone that can donate a blank piece of paper, I'd appreciate it.
Tissue paper or?
Anything's fine. Anything's fine. I don't care. So thank you so much. Otherwise. Would it? Oh no, I'm not. Okay, let's talk about my next problem. What do we want to do? We did Newton's second law, and we did work energy. What do you say? Do an impulse thing next time, maybe? Anybody got a particular one that's stirring them?
Can we do one where you have to transform back into?
Oof. See, that's a long problem, man. Most of the time, people wouldn't ask that on an exam, but. No, still, you asked for it. I don't know. Oh, now you gotta be tortured with it. Have you ever seen that? You know the song Freebird? Does anybody know Leonard Skinner Freebird? That there's like a trend when there's like somebody saying, "Hey, got anybody request?" Somebody yells out, "Freebird!" just to be a dick. I mean, it's just like it was a meme right before there was such a thing as a meme. That people will just in a crowd in any setting, someone just to be hilarious will yell Freebird. It is a very long song. And as a solo acoustic artist, when someone would do that, I would torture them by playing Freebird all the way through, every time they asked. So, I like Freebird. I heard that on the day I was driving to the airport to pick up my soon-to-be fiance. I heard Freebird as a guy. So I don't know it's free as a bird. Not any longer. I'm about to get engaged. All right, so here's an impulse and momentum problem, but it doesn't have a coordinate transformation. But we could go crazy with a coordinate transformation, but not necessarily. Or does someone have another problem they would request? Okay, going once, going twice. All right, so the idea is we've got this foot.
It's going to hit the soccer ball. The soccer ball is originally going at the foot at 3 meters per second, and then it's going to leave at meters per second, and we know the mass of it. And after it's kicked, it moves in the direction shown with the velocity at 10 meters per second. If the ball is in contact with the player's foot for 0.1 seconds, determine the magnitude and direction of the average force exerted by the player during the kick. So looking down on this thing, I think we're going to draw an impulse and momentum. So we have initial, we have impulse, and we have a final. This looks, let's say impulse. It kind of says impulse. Don't necessarily have to be spelling. Spelling is not on this exam. Wouldn't be interesting. Right? So I have this ball, and ball versus ball. We have MV1, and then we're going to apply some amount of force onto here. And we can anticipate the force is going to be in that direction right here. So we're going to say that it's going to be F. Let's call this X and this Y. Why? Because. So this is going to be the Fx delta t. We could use the delta t instead of the integral because we're looking for this average force. Right? So even though we know the force will change with time, they're asking for the average force. So we can use that. So we have Fy delta t. And this is in the horizontal plane, so we don't see any weight in there. So those are all the forces that are acting on this. And then, so when this thing is done, I'll break the thing down. I'm going to go and say that it's going to have M, V, let's call it 2x, and M, V, 2y. So we're taking the sum of the initial momentums. Here's technically the equation we're using, and summation. And I like to draw this with this because here's a pictorial and here's an equation, a model, if you will, of the situation. And so in the x direction, the x-dir, we're going to have the mass of the ball is 0.45 kilograms. And I think Dr. Alicia Garcia wrote this, so I bet that's how much a soccer ball, the mass of the soccer ball. She and I agree on those kinds of things. I like having real numbers. We're trying to find out Fx, so Fx. And it's positive, right, because it's going to the right. Delta t is given to us as 0.1 seconds. And that's going to be equal to, and we showed this in the positive direction. Well, they actually told us already, right? They already told us what this value was. So 0.45, and so this is going to be 10, but the cosine of 50. So Fx, I'm going to trust her. She would never let me down. So 42.43 newtons in the y direction. I always think wider. It's wider. It's wider and wider. 0 momentum here in the y direction. This looks like it's going to have a negative. We drew it negative, so we might we'll keep it negative. Times the force. It's going to be equal to, and then this one's negative too. So I guess I'll decide to put a negative inside the velocity there. Negative 10 sine of 50. So we're going to Fy 34.47 newtons. So if we want to find the magnitude of the force, we'll take 42.43 squared plus 34.47 squared and get 54.7 newtons. And then get the angle, take the inverse tangent of the rise, so 34.47 over the run, 42.43, and I get 39.1 degrees. So for an answer, 54.7 newtons in that quadrant down there, 39.1 degrees. Yep.
So in the diagram, the shoe is in a wider, like it looks like the shoe is only taking the force in a wider direction. So how did you?
Well, you can't quite see how the motion of the foot, right? So it's kind of like, I think they were trying to show that there was maybe a contact right in there. Yeah, instead of being directly on top. Yeah, I don't know. That's my mom tried to teach me not to you know. Fire was right.
Isn't the quadrant supposed to go in the first quadrant because the FX and FY are both positive?
Well, they're not both positive because if you look down up to here, right? I got positive values here because I assumed the direction. Because I drew this in the direction right here, right? Yeah. No, I understand what you're saying, but you got to be. You always have this choice, whether with sign conventions, are you going to assume the positive, and then if you get a negative, you know it's the negative thing, or some cases, and this is one, because we kind of, it was pretty obvious to us. So I'm not always going to be consistent in that, by the way, I'll admit. I kind of play it fast and loose a little bit, but you know, if in doubt, I will usually pick a positive direction. But if I know for sure, I'll go ahead and go with draw it like, you know, and give it the signs that I know. Yeah. The worst case is to double dip, right? To draw the thing and then, but then also use a negative.
Could you reiterate your point you made about why we're not integrating because we have like a change in time?
Because well, they're using the magical words, the average force, right? So in reality, I mean, it's going to be a split second, right? So already, I would say that if this is 0.1, pretty. That's actually a pretty long amount of time when it comes to like impulse. I mean, like, you take a look at those high-speed cameras that would do that. You know, you'd watch as the ball deforms around their foot, right, and then re-expands and then comes off of their foot, kind of thing. This thing, we're talking milliseconds right here, right? So this is 100 milliseconds is what they've shown right there to be able to get to 0.1 second. But so the time of this force right here might, like, we might have like a quick boom and then might come back down. You know, like if you could get a force sensor in between your toe and the ball, and you had a very quick sampling rate, you'd be able to get what that force time is. But instead, we just want to get what the average is, right? The force average that's taking place over there. So that's just going to be that force times delta t, right? Would give us like the equivalent. We might even think about it like in terms of this area right here, this area that we're using with this constant force that's taking place from the beginning of this is like delta t right here at that time. Does that make sense? So then we don't have to integrate because we're just trying to find this average.
So the average, like for the direction of the average force, does it need to be less than the 50 degrees that the ball is traveling?
Ooh, that's a good question. Let me think. I think so. I think it has to be because some of that force is reversing the direction.
Right.
And so I think what you're saying is right. Yeah, I think it has to be because the nature of the fact that like we're
There's a lot of that impulse is just reversing the X direction.
All right, want to try something else?
Can we do another spring problem?
Okay.
With the problem on page 17 or 7.
All right, so you're giving me a choice, so I'll say, this is a terrible diagram. I know who did that one here. It's awful. I don't mean to be so judgmental, but it's awful. Terrible, terrible, terrible. Oh, this is the boing thing. I guess we'll go with this guy. Yeah. We get all types of rotating Coast Guard professor people who have come in. They rotate in, and this person, I think if I recall who it was. I hope it's not the person. Actually, this might be. Could this be Nick? Oh, I have. No, it's not. Okay. I had one of the most handsome men I've ever met in my entire life. My wife was like, you really shouldn't be talking about how you just everybody met this guy was like, wow, that is just a nice looking guy. And he was like really smart and mild mannered, and he could draw a really good cartoon. So you know that I like him because he had the cartoon ability. I thought that was it, but he had the worst handwriting. But it's not this guy. All right, so a ball that weighs 0.5 kilograms is sitting at rest at the base of an equilateral triangle. Okay, cool, whatever. A spring, so I guess that means it's 60 degrees, right? So that's what they're trying to, I don't know why they're trying to be clever, but they did. A spring with a spring constant of 400 newtons per meter is uncompressed, okay, sure, at the base of the triangle. The cord is cut, the cord? What cord? There is a cord, all right, somewhere there's a cord apparently, is cut and the ball travels upward along the side of the triangle. The coefficient of static friction, okay, why are we telling this, between the ball and all surfaces is 0.25. You must solve using working area. Assuming the compression of the spring is 10 centimeters, okay, I see what they did. Okay, what is the maximum velocity of the ball, and what is the minimum compression of the spring for the ball to make it over the top of the triangle? Okay, so there's a number of complexities in doing this that I'm gonna I'm looking at the thing going. I have like several questions. I see right here that this is somebody else's handwriting here, has killed this part of the question, and I'm not sure if it always had that gone, because they never bring about up this cord that they're talking about. I guess we just have to go back and read through the thing and say, okay, so the compression of the spring is 10 centimeters. What is the maximum velocity? So I'm gonna, when I get to that, we have spring potential. We're good right there. Work is caused by friction, and what is the maximum velocity of the ball? Okay, so I'm trying to read what the action is here. Let me try to redraw what the actual situation is. Let's exaggerate a little bit here. So the ball is going to be right here, right there. So it's been compressed in part A to 10 centimeters. Does that make sense? That's what they're saying. They're saying the spring with this. They're showing it. They're saying that the spring, when it's fully extended, is to right there, right? And then they want to know what is the maximum velocity of the ball. Well, that's going to be right here after the spring is fully has moved, right, to its unstretched length. When the ball releases from the spring, yes. Yes. Yes, not how long the spring is, just how much it's compressed. So we don't have to use the unstretched length kind of thing that we did in many other problems with spring, in this particular scenario. So just coming from this right here, I'm just going to from here to here, right there. This is going to be our delta y that's being experienced in part one, problem one. We also want to have, because they told us about friction, we probably maybe want to do like a little bit of a quick FBD, IBD, just for the sake of it, X prime, Y prime. We kind of know from having done this a bunch of times on slope things what the answer is going to be, but I think it's worthwhile. And I don't like the fact that he was using friction in a ball like this. That's not really how balls work in friction. It'd be better if this was a block. So there's an invalidity to what he's written, and this is what you get for having rotating, Coast Guard officers that all of a sudden have to become professors, and they've never been a professor, and they're only going to be a professor for 5 years, and then they're going to go do something else. But we love them anyway. So, but this has flaws. I would make this into a block, because a ball would roll and wouldn't have like friction like this thing is saying it is right here. But we can see that we have the weight of mg of the ball, and here's our theta, and we know that theta is equal to 60 degrees. And depends where the ball is in this whole process of what its acceleration is. Maybe I can go ahead and put a spring force in there. So I'm going to say that it doesn't really matter, but all I'm using this for is in the y prime direction, just to get the normal force, because I need it. Fn minus mg cosine of theta. So Fn is 0.5, 9.81, cosine of 60 degrees. And I don't trust him, so I'm going to go 0.5. Trust issues. Yeah, okay, you got it right. 2.453 newtons. So my friction force, they told me coefficient of friction was 0.25, 2.453. Doesn't seem like enough. 0.613, did I get that wrong? 6131? Didn't feel right. 2.453, 0.25. Yep, that was right. Okay. All right, so that was just some preliminary stuff over to the side. Let's have our kinetic energy and potential energy and work and kinetic energy and potential energy. All right, so kinetic energy is state one. That's okay. That's going to be down here. And that's going to be equal to 0, because they're going to push this thing down 10 centimeters, and we're stopping there. The potential energy at 1 is going to be the spring being compressed. And they gave a spring constant of 400 newtons per meter. And I got to tell you, centimeters drives me freaking nuts. So I'm going to 10 centimeters is 100 millimeters, which is 0.1 meter, right? I have to do that. I can't go from centimeter to meter. I just can't make myself do it. I know, shut up. I'm not smart. I'm not a smart person, right? But I can't do that in my head. Centimeter, it just is like this mental block. I didn't mean to tell you to shut up. It was a friendly shut up. It was the kind of like, I feel as though we're comfortable together enough that I could tell you to shut up. Yeah, no, I didn't mean it though. I'm not sincere. I just would not. It's not nice. I try to be a nice person. which is really fighting against my nature. Just it's not in my nature to be nice. Come from a long line of not nice people. So we're going to have the friction force times the distance this thing is going to move between states 1 and 2. We just found that friction force of 0.6131. And we're moving, as we said, 10 centimeters, which is apparently 0.1. Okay. Just divide 10 by 100. That's all I need. So 0.06131. That's not very nice. Newton meters. And then KE2 is really what we're trying to find, right? 1/2 MV2 squared. And then the last one is PE2. And so that's, we're going to say like this is the datum right here, right? This is the datum. And I guess I could write the delta Y over to the side, but we're going to go mg delta Y 1 to 2. So it's 0.5, 9.81. And that's going to be 0.1 times the sine of 60. So 9.81, 0.5, 0.1 times 60 sine times. So we get a pretty small number, 0.4248, call it Newton meters. Plug them back up in the top. 0, 2. I guess we could make it negative out here. I really like parentheses here. I don't know if you noticed. 0.5 V2 squared plus 0.4248. V2 is therefore going to be, let's see, subtract that out. Subtract that out. Subtract. So 2 times, then 0.5. That was pointless. And square root, and cross your fingers that we get 2.461 meters per second. And they wanted the velocity. So that means we got to get ourselves a vector. Velocity. And I wrote really big, so I need another piece of paper to go to part B. We're going to find the minimum compression of the spring for the ball to make it over the top. See, I think that they have made a problem that is more difficult than they think. Yes, they did, because you have to use a quadratic. Ooh, this is cruel. Like, this is what you get with amateur problem writers. You go, oh, that doesn't be too hard, and then you guys, nobody finishes the exam because the problem's hard. I remember, I seem to recall actually having this whole conversation about this problem. You know that then everybody's going to be able to finish this damn thing. Okay, well, okay, so what we have to do here to try to approach part B, what is the minimum compression of the spring? I think it's best to draw another, that looks like a terrible triangle, thing here and set it up. All right, so we're going to have, it's got to reach up to there, right? So that's how high this thing needs to go. And here's like the bottom. And here, so here's we're going to go to the datum. Yep. So it's the kinetic energy at state 2. We could actually call this 3 if we want, but everything needs to be reset, to tell you the truth. because it's going to be at the bottom is going to be a new compression, new amount of compression right in there. So I'm just going to call it 1 and 2. And this del I1, 2 is going to be in part of it. All right, so we could, yeah, I guess so. It's going to be the height of this thing. So they told us this thing was 1 meter wide. Therefore, this is 1 meter. I said the height of this thing is going to be 1, well, I don't want to say that. I really want to go 0.5 divided by the cosine of 60. Did I make that more difficult than I needed to? I think I did. But it's going to be plus, and here's the thing we want to try to get. We want to try to get the del 1, right? So it's got, not only does it have this height part of it right here, which is what I just did, but it also has this height change. So that's sort of a pain in the ass. That del 1 that we're trying to find, and times the sine of 60 degrees. Did I do that right? Yes, yes I did. Okay. No. Yes, no. All I needed to do was, yeah, I did make that too complicated, right? All I need to do was multiply 1, because this length right here has to be 1, times the sine, you moron. 1 times the sine of 60 degrees. I wonder if I would have got the same thing. I think I would have, maybe. Okay, sorry about that. Oh, I'll try to do less thinking. All right, so let me write out this main equation here. So that's a good place to start. So KE1, 0, right? If you even say KE2 is going to be 0, let's write it, might as well. Because it's going to go here, it's going to, we want to find it just how much we have to push this thing back just to get it to move. Now so the PE1 is going to be 1/2 K del 1 squared, right? Del 1 being the thing that we want to try to get. The work now is going to be negative friction force times this entire distance, which is going to be 1 plus del 1. All right, so write that out anyway that we want to do. I guess we just left it that way. Yeah. We wrote the friction force somewhere. 0.6131. And then 1 plus del 1. I'll just leave it like that for the time being. I think that's true. Yep. And then PE2, just as I've put it onto there, is going to be the mg times, actually we just say 1 plus del 1 times the sine of 60, right? Because that's what we essentially have right up above. Right? So you can plug all those in. 0 plus 1/2 K is 400 del 1 squared minus 0.6131 1 plus del 1 equals 0 plus 0.5 9.81 sine of 60, and then 1 plus del 1. And what we're going to find, we're going to get a quadratic, right? So 200 del 1 squared, and we'll get, let's say this one right here, 0.5, 9.81, and sine of 60, and 4.248. So that's going to come back and come over onto this side and make that it be negative as well. So it's going to add together. Woo, watch it. This is true here. Okay, cool. And so 0.6131. So we're going to have a negative 4.861 del 1. And then this 2 is going to also be negative. And that's going to be negative. So this is going to be negative 4.861 equal to 0. And of course, your calculators, I'm sure you know how to use your calculator to get this whole thing. But me, I am too old to learn something new. So it's negative b plus or minus is already negative the square root of 4.861 squared minus 2 times a, 200, c, which is this is negative, so that's going to make that plus. That was nice. We don't have any chance of making this an imaginary number. Divided by 2a. So 2a. And should be able to get 2 roots out of that. Squared, flip them, and then 2 times it, and 200 times it, and plus take the square root. So I'm going to get 4.861 plus or minus, 40. That's huge. That doesn't make any damn sense. That can't be true. I did something wrong. I don't want to waste our time here, but that's okay. I still 4.861 squared. I have 400 times 4.861. Wow. I guess that's right. Add them together. Square root them. Yep. 44. That seems huge. 44. 8. 6. Oh, I see why. I'm going to divide by 400 again. So for the positive one, 4.861 plus 400. So we get 0.1243. And then the other one, we're going to get a negative value, which is meaningless. That's the whole reason why I wanted to actually get the thing. 4.861 minus 400. So we're going to get a negative, really small. I guess it's pretty much this. Yeah. I'm sorry if I went off the page right here. But, so this is meaningless. So the del 1 is 0.1243. Whoop, got a different value from him. Shit. I must have done some math wrong. He says that it is 0.168. Huh. And all the other stuff is the same as him, right? You got the 200s I did this from. It says him, but actually it looks like Alicia's handwriting. I don't know.
Yeah, but on the other one,
Yeah, so, but this is -2. This is, this,
-2, yeah, okay.
so I'm at that there now. I don't know. People usually, you guys usually have root solvers on your calculators, right? That you usually don't use the root solver on your calculator. Oh, there you go. Thank you. Appreciate that. Yeah. Thank you. I should learn the root solver on this calculator here. I'm sure there is one. I don't know. My virtual 42S. I use a 35S because that's allowed on the FE exam. That was my conclusion. I should use that. So anyway, this is the answer right there. Don't want to waste your more time with me struggling with math. All right, what kind of problem want to do next? Anybody on any of our remote friends got a request? Anybody still there? Yeah, Joe and Olivia are. Okay.
It's page 8 with the ball that dropped onto spring. It's an impulse momentum.
This might have some potential energy in it too, I think. Well, it's also projectile motion, kind of a little bit. Not really too much of it, but some. All right, so where did you go? Is it early on? Early on? I know you were in here. Where did you go? I just want to make sure I have it when I get to the thing. Right. Well, then be that way. I guess I don't have it in there. I've looked through every page. All right, it's an adventure. I look into my. Come here, computer. Oh, it's me. Switch me. Come on. There you go. I don't have to talk to it. You just have to see my face. But I feel as though I have to talk to it. Have this conversation. That's the only way it'll work. Right? Is if I can get in there. Let's see. Exam prep and exam. All right, so you must use impulse momentum to receive full credit on this problem. The 75-gram ball is projected from a height of 1.6 meters with a horizontal velocity of 2 meters per second. And it bounces from a 400-gram smooth plate supported by springs. Knowing that the height of the rebound is 0.6 meters, determine the velocity of the plate immediately after impact, the coefficient of restitution E between the ball and the plate. Interesting. No, I think she wrote that out. Okay. So first thing to do is to find what the velocity of the ball is just before it hits the plate. That would be a good thing. And so to do that, we could actually use work and energy, to tell you the truth. We could actually probably do impulse momentum. That would be an interesting thing. I guess we could, as a demonstration of being able to do it.
Use our special equation, the v squared equals v naught, because our acceleration in the y direction is just gravity.
Yep, we could do that. They'll all get us to the same place. We could say that like in the y direction, that the velocity, it starts out, we get the velocity at, I guess I'll call this state 1, state 2, state 3, state 4, maybe. So state 2 in the y direction is going to be the velocity of state 1 in the y direction, e squared, minus 2g, and then we'll go delta y. You got to be careful here. The delta y is actually negative. So when we go to do this right here, just be aware that we're gonna have a 0 right here, starting out with a y velocity of 0, but it starts out with a high position to a low position. So this is actually a negative value. So don't be concerned there if you get the wrong. So we can find that v2 is going to be the square root of 2. This is 9.81 and 1.6. So even if we wanted to, we could go negative there, but that would be negative right there as well. So let's see. Come on, stop it. 9.81 and 2 times 1.6 times square root. So I'm going to get that it's going to be 5.603 meters per second just before it hits the bottom right there.
Why do we consider that has to be negative?
Because we're going from position 1 to 2, so we should have position 2 minus position 1. All right, so this delta y should be y2 minus y1. y2 we could consider that 0. y1 is 1.6. All right, so if we're trying to keep the sign conventions correct, that's what we would do. Okay, and then we could also do the same thing before for V3, right? So the velocity of state 4 in the y direction squared is going to be equal to the velocity of 3 in the y direction squared minus 2, and I should have said that this was states 1 to 2, g delta y, and then we go 3 to 4, right? And so this is going to be 0, right? Because that's the height in the y direction is reached. And we're trying to find this guy, minus 2, 9.81, and it reaches 0.6 meters. So, and I guess that should still be y direction. So V3 in the y direction should be equal to 0.6 to 9.81 times, but we got to take the square root. Should be 4.202 meters per second. Uh-oh. What did I do? How come I got the wrong number here? 2.6. I should get the same exact thing, and I must have just hit the calculator wrong. 2 times 9.81 times square root. Sure enough. Ooh, don't do that. .431. I don't know why. No, okay, so both of these are in the y direction, but they're also in the normal direction. If we were to take a look and draw the plate out right here, right? That's where, when this thing is coming down, here is where it contacts, right? So that would be the normal. In fact, actually, I should probably draw this thing out. So here is the initial. Here's the impulse. Here's final. Kaboom. So this is going to have an MV X, I guess an M. Let's see, what are we going to call this? There's a ball and a plate, so this is going to be B. And so this will be B. I should have called this all B all the way around here. B2 X, and then right here should be MB VB2 Y, equal and opposite for the impulse. And then I think we can go ahead and guess that the plate's coming down, so the mass of the plate times the velocity of the plate, and this is going to be at state 3. And we could go ahead and guess that the ball is going upwards. That's fine. M B V B 3 Y, or normal. I should probably call it normal. We could just know in our heads that it's going to be normal. You can call it normal or whatever, or tangent. Normal or Y. Let me see. This is going to be because the I'm having a weird time here. It says we want the velocity. Okay, we know the coefficient. We know. Oh, okay. I got you. Okay. Excuse me?
If we want to find the velocity of the plate after, why aren't we knowing what it is before?
Because it's not moving. Before the ball hits it, it won't move. So it's 0. So we're doing the sum of the moments at state, I guess we decided to call it 3, plus the force dt, right? Moving from state 2 to 3 here, equals, kind of getting in the way here, sum of the momentum at state 3. And so we do this in the y direction. And so we're going to have our 75 gram ball. So that's 0.075, right? All those things would cancel, by the way. So, I mean, it's not 100% necessary, but I think it's a good idea to use the correct units onto the thing. But I would imagine Alicia just left it as grams, but we just don't always agree on things. This would be 2, so it's 5.603, and let's see, nothing there. Okay, so this must equal, so we're going to have positive 0.075 times our, where'd you go? 3.431. But then I guess I could put them here. I could put the negative here if I wanted to, but we know that the plate is 400 grams, so it's 0.4. And then we don't know this. The velocity, that's what we want to try to find, the velocity of the plate at state 3. And if I did everything right, it should be 1.694. Yep.
For the impulse diagram for the final, how come there's no like X component?
You're right. And we should remember that's the tangential direction as well as the X direction, and that they're going to be equal to each other. we weren't asked anything where that's going to come in, but you're absolutely right. It belongs in there for completeness.
Is tangential always going to be equal before and after equals? Like,
Yes, yeah. Can't think of a scenario that I could create where it wouldn't be, but we won't play any games along those lines. But we could probably, in the real world, come up with one where it'd be like, I said that if you had, well, these are particles, but if let's pretend that they could spin. If there was like a rough surface and it could spin, so like a tennis ball being hit with spin at Wimbledon, where it can grab a hold of the grass, or even at the French Open right there, where they can go into clay, they can make the trajectory of the ball difficult to judge with that spin, because in the tangential direction there is an impulse, but not for our purposes. All right, so this is supposed to be negative right here. My bad. As I drew it, we would find it, we would get a negative value right there anyway. But yeah, so that's going to be over to the side right there. So that'll collect, and we'll go 0.075, and then 5.603, 0.075, and we're going to add those together, but then divide by 0.4. So yeah, so I should get VP3 is 1.694 meters per second, which is the same thing as Alicia got. And then we also want to get the coefficient of restitution. I don't think we need, we did need that thing we just got. Okay, good. So remember that the coefficient of restitution, we could write it out in the with the normals, but let's see. Let's write it out with the way that we have it written out. We're going to have V plate 3 minus V ball 3 Y divided by V ball 2 Y minus V plate 2, which we know is 0. So the plate has a negative velocity of 1.694 minus, and I hope I got that right. Yeah, no, I think I'm going to be okay. And this was, we found this out to be 3 point, no. Yes. 3.431. And divided by, and then this one's downward, so that's why it's negative. So it's negative in here. And let's see where we're going with this. See, it was the 5.603. So 3.431. Whoops. Add them together. And 5.603. Oh, good. Got the right answer. 0.9147. All right, so they asked for velocity. And they asked for our coefficient of restitution, 0.915. How's our home team doing? Oh, well, and then there was one, Olivia R. Any requests? Problem type? Song and dance number? I'm playing in Uncasville tomorrow. Uncasville. Where the casino is. But not playing at the casino. I haven't played the casino before. Felt like a job. Did not enjoy it. Okay. Absolutely. Page 4. Yeah, cool. Let me see. Should be back in the order here. I might rescan these solutions. I don't like the way they're written, some of them right now. I prefer my way. Okay, so we have these kids on this little swingy thingy, a little carny ride. Carny, do you accept this challenge of shenanigans? That's an early South Park episode. Don't see the spelling there. There we go. All right, so determine the constant speed of the passengers on the amusement park ride if it is observed that the supporting cables are each directed at 25 degrees, so that's the angle they're saying right there. From the vertical, each car, including its passenger, has a mass of 80 kilograms. So this is a path coordinates problem, and they've actually already drawn out what the they decided to call this B1. I like to call it, I don't know, K or even Z sometimes or whatever. So like looking down at the thing, you know, if we were to take a look at one particular thing, here's the tangential and here's the normal direction. But that really doesn't do us a whole lot of good. It's going to do us a lot more better to take creepy eye and look from this direction right here. And if we do that, we're just going to represent them by a ball. Take an FBD and an IBD. And now the normal direction, maybe I'll go EN right there. And in this direction, I'm going to call it K because I don't like the way, I don't like B. I don't like having the B in there. We take a look at that, we're going to see the tension FT is going to be in that direction. And they gave us this angle right here, so this is going to be the same angle right in there. And then we're also going to have, and this was in US unit, I mean SI unit, says MG. And looking at this now in the IBD, the only acceleration is going to be towards the center, right? Just like up in here, the acceleration is towards the center. We're just looking at it in a different view. So we're going to have M, A, N. It's going to be in the normal direction. So the problem here for us that we're faced with is we don't know the tension, but we do know the angle. So our strategy here is let's see what happens in the Z direction first. So if we get the Z direction, because there's no acceleration in the Z direction, right? We'll be able to find what the tension is. So now, in the normal direction, knowing the tension, we'll be able to figure out what the acceleration is. And knowing the acceleration, we'll be able to figure out what the velocity is. So we say sum of the forces in the Z direction, mass times acceleration in the Z direction. We know it's 0. So we'll go Ft cosine of, I'll use the numbers, 25 minus 80 and 9.81 equals 0. So the tangential is going to be 80 times 9.81 divided by the cosine of 25, or 865.9 newtons. And then, so knowing that, we take the sum of the forces in the normal direction, mass times acceleration in the normal direction. Positive is over that way. We're going to get that tension, 865.9, but now it's going to be the sine, because we want it to the opposite from the mouth of that 25. It's going to be equal to, and we're going to see that it's going to have 80 times the normal acceleration. I should point out that we could have combined this problem together, and we can see that 80 would have shown up over here on the left side, and the 80 would have been right here. So the angle didn't even actually, the mass didn't even affect what this would be, but we're doing it step by step here. And divide by 80, and we get it's 4.574 meters per second squared. And we know that it's v squared divided by rho, or call it r. And now we actually, for this rho, or r, we need to do a little geometry in there. So we kind of notice that ahead of time, that we're given this length, we're given this angle, but we have to remember it's towards the center. So it's going to be 4 plus the 6 times the sine of theta will give us that full distance of the young lady to the center, right in there. Right? Rho is going to be 4 plus 6 times the sine, okay, 25. So that's 6.536 meters. So the velocity here, square root of 4.574 times 6.536. I should get 5.468 meters per second. And it says, determine the constant speed. So we do not need to make it a vector.
Why don't we include mass?
Well, I did include mass, but I said that we didn't have to. Because you see right here, we were solving for Ft right in there, but you could just see that this would have been mass times gravity divided by the cosine of 25, right? And would have been brought over here, so it would have been that times the sine is 25. It would have had mass in it, but then we had mass over here on this side, and that mass would have canceled out.
Oh, okay, so if we add mass, that would be, we wouldn't want to do that. And the sum of forces in n equals n, we sort of rho, because the acceleration equals the sum of forces in the normal. Is what we found?
Yes, but I'm not sure what you just said, though.
I was writing it out ahead of time, and I just divided by the 80, the mass, because I was just using the equation of sum of forces of n is equal to mv squared as well. So I was a little confused about the mass. So like, why we didn't include it?
We did include the mass.
Oh, I mean afterwards.
Afterwards.
In the last step.
In the very last step, I solved for this acceleration, right? And then from that acceleration, we're just trying to find what v squared is going to, what velocity is going to give us that acceleration.
Right.
Okay.
I made it more complicated.
No problem.
Thank you.
I'm here to try to uncomplicate.
Could you show the trig that you did to find the rho?
Oh, this guy?
Yes.
I'm just looking for it from the side, right? So it's, you know, a side view of this thing, like that right there, right? So this is 4 meters up to here, and this length was given as 6 meters. So I want to find this little segment right here. So that's going to be 6 times the sine of theta right there, right? Where theta was given right here. So that's going to give me the opposite length from here. So it's going to be 4 plus 6 times the sine of theta.
How does it give us a total length?
It's not the length. We want to have the distance from here to there.
Oh, I see.
That distance right there. So because this thing has a straight arm and then it has a slope thing right there, we need to add that 4 with 6 times the sine of theta. No problem. I can keep on going if you want to have more questions. Bueller? Yes, sir. Welcome. Have a great weekend. All right, so this block A is 20 kilograms, and it's on a sled that's 40 kilograms, and both A and B are initially at rest. B rests on a frictionless surface. Okay, that's good. When a 200 Newton force is applied to sled, right here, B, A is known to slide along B. All right, so that means that it's overcome any coefficient of static friction. What is the total acceleration of block B? Magnitude direction, you must show FBD in inertial diagrams. What is the total acceleration of sled B? You must show this. And how long does it take A to slide 2 meters along the sled, right? So that's a good, this is a good little combination of problems together. Makes you think a little bit. So probably best to do separate FBDs and IBDs of each of the pieces. All right, so we're going to have FBD and IBD of these. And we'll have, here's our X and Y. You're welcome anytime. We're going to have MAG, and we're going to have FNA. And we have to decide on our friction direction. We'll see which direction friction is going to go. Well, let's see. First off, I don't want to commit to this just yet, and I don't know about the acceleration here. I think this thing wants to stay in place, but by moving this, you too, it's going to have this friction force right here. So we're going to say that's the friction force A. And because of that, it's going to move MAAA. You see my logic there? Starts at rest. This thing gets pulled. It's going to move to the right, but it's the friction that's going to cause it to move to the right. So this right there. I might want to leave a gap in here. I wish I had like made all this smaller and made it over to the left instead, but we'll do an FBD and an IBD of the plate now. And I wish I had made a little bit more room in there. cool, right there. So we have our 200 newtons applied right there. We also have the force FNA, and we also have, you see, it's got to be equal and opposite. We're also going to have the force FFA right there, acting onto this. We're also going to have FNB, but fortunately there's no friction on here, so I think we're good. We also have to wait, whoops, we need the weight, but I don't think it's going to matter to us, so it's going to be MBG. Still. And this guy's just going to have acceleration here, so it's an MBAB. And setting up a free body diagrams and drawing them is a huge part of doing this. So getting just to that stage will get you buku points. The problem is this one is 6. I don't see him. Where did he go? Just want to make sure it's doing it. There it is. So up above, up here, I get the sum of the forces in the y direction, mass times acceleration in the y direction. We know it's not moving in the y direction. So we could just write FNA minus MAG equals 0. No kidding. It was going to be 20 times 9.81, which was always going to equal, I don't like his, I remember this is Nick Parker's. He was the beautiful man. This is his terrible handwriting. 196.2 newtons. So the friction force of A mu FNA is going to be 0.3, 196.2, 58.86 newtons friction force on there. So we know that it slides. So I wish I had made more room in here. I'm going to continue down some of the forces in the x direction, mass times acceleration, the x direction, right here. So knowing this friction onto here, we could find that the A is going to be FFA, only force in there, equal to mass times acceleration of A, so 58.86, and the mass was 20, so we'll get the acceleration of A is just going to be 2.943 meters per second squared. Now we go to this FBD and IBD and say the sum of the forces in the x direction, mass times acceleration in the x direction. And the only forces that we have the friction force and the external force right here. So we're going to have, I'll make the external force because it's positive and the positive x for us. Define that as positive. Minus our 58.86 equals, and then we'll have a mass of this is the 40 kilograms. So the acceleration of B is going to be 200 58.86 minus 40 divided, we should get 3.529 meters per second squared. And the last part of this was asking, how long will it take for block A to slide 2 meters along the sled, right? So both of these are positive values, but we want to have the acceleration of A with respect to B. And if we write that out, that's going to be, we'll make it a vector, acceleration of A minus the acceleration of B, right? So this is going to be on the sled because it's with respect to the sled. So that's going to be our viewpoint is being on the sled if we're with respect to B. So we end up having that it's going to be 2.943 minus 3.529. So we end up getting a negative number, but that's actually what we kind of anticipate, that it's going to be in the negative direction for us. All right, so we end up with a negative 0.5855 meters per second squared. So they ask us how long, so this amount of time. So what we would find is we'd have x, let's call it A with respect to B, is going to be XA with respect to B, right? But we're going to do the delta, so bring them over anyway. So we could just say that's going to be 0. Plus the velocity, initial velocity of A with respect to B, times time, but it's starting from rest, plus 1/2 acceleration of A with respect to B, that's something we know, times t squared. So they're asking us, and it's going to be moving in the negative A with respect to B distance direction. So that's we can say that when we say that it's going to be 2 meters, it's going to be a negative 2 meters that it's moving, and 0, 0 t, so that didn't matter, plus 1/2 negative 0.5855 t squared. We're going to find that the time is going to be equal to, so let's see, we're going to divide this by 2, and we're going to also multiply by 2, divide 2 by that, and then take the square root, and so we should get 2.614 seconds. Make sense? We're still recording? You're still recording here? Olivia, you're still here? I might keep these and actually replace my other solutions with them. A little at a time. A little bit at a time. The full collection of these. All right. Any more? I can keep on going if you need to. You're welcome. Have a great weekend. I hear you. It's only so much. I saw the associate provost on the way over here, and I said, I'm going to see you. It's a question of stamina. Who could last longer? Me or them? Miles?
Yes,
Any questions?
no questions. Thank you.
You're welcome. Olivia, you there? Do you have any questions? Anything, any requests? Okay. Okay. Well, I'm gonna call it then because it's Friday, you know, and I gotta go write an exam and grade some shit stuff. I gotta play some guitar at some point today. Gotta sing. I gotta practice get my voice. Yeah, terrible band.